All right, class, welcome to the next week of class here in Lecture 6. We're going to remind ourselves about some of the mathematical structure of thermodynamics we've been building and understand a little bit more of their implications. This will take us down a path where we'll remind ourselves of a few concepts you probably have been exposed to in introductory thermodynamics courses, some other well-known functions that have utility under different sorts of constraints, and we've discussed thus far. And we'll be able to use that structure to make some specific statements about how systems respond and relax to equilibrium. So that'll be the focus of today's lecture, really fleshing out more of that mathematical structure and its implications. This will lead us back into a discussion of the microscopics next lecture, where we start putting the pieces back behind the microscopic structure of these underlying microscopic descriptions of these thermodynamic quantities that we're introducing. All right, but to begin, let's remind ourselves of some of the things we discussed in the last couple lectures. One of the most notable results we arrived at last week was a microscopic description of the first law. That is just a statement that energy is conserved, our old bookkeeping statement. Said in a more interesting way, energy is conserved because it can transform through two different fundamental sorts of processes. What we've denoted as dq and called heat, and what we've denoted as dw, what we mean by work. Now note, dE on the left-hand side is written with a normal d, that's an exact differential. It's treated with the normal rules of calculus. The dq and dw's are so-called inexact differentials. Their changes depend on the path that I take through the system. So all of you who, for which this concept is still a little fuzzy, I would suggest going to Daniel's discussion section notes, which he discussed last week. And those are posted in B courses. Now, heat and work, those are two ways that energy can change, and their distinction is really in our ability to control those processes. So work are those manipulations to the system that changes the system's energy that we affect on the system directly. We control some parameter in the system, like a mechanical property, and affect changes of the energy. Heat, by contrast, are those changes in the energy that we do not directly control. Those are the fluctuations of the surrounding solvent or gas that exchange energy with the system through processes that we don't have a handle on directly. So that's the first law. In the reversible limit, so if I affect a change to the system in such a careful way such that I proceed through a series of equilibrium states, we can write down the first law, changes in energy, as functions of thermodynamic variables. So specifically the heat can be written down as the temperature times a change in entropy. And the work some force dotted into some change of a mechanical variable. So again, TdS is the reversible limit of some heat, and F dx, some reversible change of the work. So apart from the first law, we refined some statements of the second law. Specifically, we deduced a statement of the second law, originally due to Clausius, for a system that can exchange energy with the surrounding heat bath. So Clausius's statement of the second law valid for an open system with a bath at some temperature T says that the change in the entropy of the system is necessarily greater than or equal to the heat released by that system divided by the temperature of the bath that it is dissipating that energy to. The reversible limit is then that the change in the entropy is equal to that dissipated heat. From that statement due to Clausius, we arrived at a statement about the means by which we can do work on a system, and specifically that the amount of work done on a system is always greater than or equal to the work done in the reversible limit. So if I want to affect a change to the system by doing some work, the least amount of work that I could ever do is that which happens reversibly. Now I'll note that in all of these statements, macroscopic averages are implied. Namely, these are statements true for macroscopic systems, where the numbers of particles are large and behavior is dictated by the typical behavior, by the average behavior. As we saw when we simulated that polymer pulling experiment, there are, from one realization to the other, to another, on a microscopic system, that heat and work are fluctuating quantities. And thus, these statements of the second law are really statements microscopically about averages. The average work is always greater than the reversible work, which is not an average, that's a definite quantity. The average change in the entropy is greater than or equal to the average heat released. Finally, this statement of reversible work led us to a definition of an old friend. We introduced the Helmholtz free energy. Only ever reasonably denoted as A. A was equal to E less than T minus S. So the Helmholtz free energy A is equal to the energy minus the product of temperature times the entropy. That function, the Helmholtz free energy, is a so-called natural function of the temperature and the mechanical variables. If I ask for changes to A at fixed T in the mechanical variables, then a spontaneous process, or a statement of the second law, another statement of the second law, is that the change in the Helmholtz free energy is necessarily negative for a spontaneous change. dA at fixed temperature is exactly given by the reversible work. And so that is indeed why we call it a free energy. It is the amount of energy stored in the system that can be extracted as useful work. Its identification as a natural function of T and X implies that if we ask for differential changes in the Helmholtz free energy, that it comes from differential changes in the temperature, in this case times minus S, plus differential changes in a mechanical variable times their corresponding forces. Often, for the kinds of chemical systems we're interested in, we are imagining doing work as PV work. So we have a pressure times a differential change in the volume, plus chemical work, the chemical potential mu times differential changes in N. All right, so that's where we've been. I want to start by expanding a little bit on the manipulation that leads us to this definition of the Helmholtz free energy, namely the structure, flesh out the structure a little bit more of the so-called Legendre transform of the energy that yields the Helmholtz free energy. Okay, so indeed we have identified the Helmholtz free energy A as a so-called Legendre transform of the energy. And what that means is that A, which is defined as the energy, which is some function of the entropy, in addition to mechanical variables, which I will not denote here, less the entropy times how the energy changes with entropy at fixed mechanical variables. This, of course, being nothing other than the temperature. So then, again, that equality is just defining the Helmholtz free energy as we have before, as the energy less that entropy times temperature. So what does this mean? Why do we define it in this way as some function, the energy, less a variable that original function depends on, the entropy, times the slope of the original function, the energy, with respect to that variable, the entropy? So why on earth would we do that? Let's consider a function f of x that I can plot. So f of x as a function of x, maybe as a curve like that. Let's denote some point on that curve, x naught, located there. That point I can draw a tangent line on, which is nothing but the slope given by the derivative of f with respect to x evaluated at x naught. Let's define that slope as a function y evaluated at x naught. Or more generally, let's define the function y of x as being how f changes with x. Okay, so we have a function, f of x. We could take its slope at any point on the x line, and let's define that slope as y of x. We could construct an auxiliary function call it g, which is equal to the original function f minus x, the variable f depends on, times y, the slope of f with respect to x. If I ask for differential changes in this auxiliary function g, that occurs through changes in f, which change with x, times changes in x, minus changes in x times y, minus x times changes in y. That's just the chain rule of the definition of g. Now, df dx is what we defined as y. So we have y times dx minus y times dx. These cancel, leaving us with changes in g coming about through minus x times changes in y. So we would say that g depends naturally on y. While f depends naturally on x, this new function g depends naturally on y. That means that if we ask for how g changes with y, there's a simple variable that reports on that, in this case, minus x. Now notice that if I took g and I added back x times y, that is equal to g minus, this relationship tells us that x is equal to dg dy. So I have the same as, so I could substitute in for x minus dg dy times y. that is then the same as f. So this structure of being able to define that is the same as f because I defined g to begin with as f minus x times y. If I move that x times y over to the other side, which I am free to do, g minus x times y is equal to f. So note that there's the same structure going forwards and backwards. I can construct g by taking some original function, subtracting off this special pair, the variable that it's a function of naturally x times its slope. Alternatively, I can reconstruct f by taking this auxiliary function g and, in this case, positive sign, and adding back the variable that is a natural function of y times its slope with respect to that variable, in this case, minus x. That seems like maybe some trivial algebra, a trivial differential calculus, but it encodes something pretty powerful. It encodes that this transformation, g goes to f or f goes to g, is invertible. Namely, I can go forwards or backwards without losing any information. That's an algebraic way of thinking about this Laplace transform. What have we actually done graphically? How is it possible that f and g contain the same information? Well, again, if I plot f of x versus x, some curve, the function g is nothing but some value of x, say x naught, and its slope, or its slope, the slope of x evaluated at some point. Let's draw this a little more carefully. So let's evaluate the slope at this point. That's some line. That line has slope y by definition. There is some intercept back on the x equals 0 line. Let's call it g naught, which is f less than x naught times y naught. So in fact, what g is doing is it's constructing f. It's got all of the information of f. By noting two features of that curve, namely the slopes and intercepts at every point on that curve. Through knowing the slopes and the intercepts, I can uniquely reconstruct f of x. So said again, I define a function, I have an original function f, I define a new function g, which contains the same information as f, just rewritten in a different way. In this case, it's written in a way that reconstructs this initial curve, f, by knowing the slopes and intercepts of that curve for all points x. Thermodynamically, the Helmholtz free energy is that same structure written in terms of energy and entropy. So energy is some function of entropy. A point on that curve, say evaluated at S naught, has some corresponding tangent or slope. That slope is dE ds, which is nothing but the temperature. In this case, at S naught, call it T naught. There is some associated intercept, if I extrapolate that back to zero entropy, which is given by the height of that curve, E, evaluated at S naught, minus T naught, S naught. So E less T times S is what we defined as A. So A is nothing but recasting the relationship between E and S as one in which is convenient to state when I'm not manipulating S directly, but rather I'm manipulating the temperature. Now, there's a bit of a subtlety here. I've drawn those curves E versus S or F versus X as smooth, as convex functions, monotonically increasing functions of their arguments. You could imagine that if that f of x were more complicated, it had wiggles such that those slopes intersected at multiple points, this relationship would not be so straightforward. I could not uniquely determine the energy as a function of the entropy or as a function of the temperature instead of as a function of the entropy. However, we'll argue slightly later in this lecture that it must be the case that those are smooth functions. In fact, for a macroscopic system, the stability of equilibrium, we'll see shortly, dictates that E versus S is a convex function, that E as a function of S is in fact convex. At least away from very special points where E versus S can exhibit singularities. Those are what we call phase transitions, and we'll consider quite a lot at the latter end of this course. But for now, away from special points, it is guaranteed that E is a simple function of S. In fact, it is a convex function of S. So then, again, just to reemphasize, the Legendre transform is essentially parameterizing the curve E versus S by knowing its slope and intercept for all points S. So if we take a step back, we started on the very first lecture with a very simple object, what we denoted omega, which depended on energy and some set of mechanical variables and was nothing more than a counting function, a function that counted up all of the microstates consistent with that energy and set of mechanical variables. So an intrinsically microscopic computable quantity. From that, in Boltzmann's definition, we made contact with thermodynamics by saying that the entropy is nothing but the logarithm of that number of microstates, noting that both spontaneously increase in a probabilistic statement of the second law. The fact that E and S have simple relationships, that E is a convex function or S is a convex function of E, means that S as a function of E is invertible, and I can write E as a function of S. And what we've just learned is that whether or not we think about the energy or the Helmholtz free energy, A as a function of T and X, we've not lost any information. We will see in the next lecture more explicitly then how A embodies microscopic information. Right now that we know in principle it must, because we can bootstrap our way all the way to the Helmholtz free energy from omega. If we always had to do that, that would be a little cumbersome. In fact, we will find that there is a simpler microscopic expression that is a little bit more direct that teaches us about the relationship between the microscopic underpinnings, the microscopic degrees of freedom of some system, and its associated Helmholtz free energy. So stay tuned for that. Before we go there, however, I want to think a little bit more about this structure of thermodynamics and flesh out a couple other useful properties and generalizations of the sorts of things that we've been discussing. So first, let's think about other so-called conjugate pairs. We have introduced one conjugate pair, the temperature and the entropy. They have a special relationship because the temperature is defined as how the energy changes with entropy. There are other sorts of relationships. For example, if we ask for how the energy, which is a natural function of the volume, entropy, and number of particles, if we ask for how the energy changes with volume, holding the other two fixed, that is a definition of the pressure. So in the same way that the temperature and the entropy are so-called conjugate pairs, we would say that the pressure and the volume are conjugate pairs. The energy could be manipulated by changing the number of particles at fixed volume and entropy, that yields a definition of the chemical potential, and thus we would associate mu and n as conjugate pairs. They form a specific relationship in regard to the energy. So in fact, we could use either of these pairs to construct additional Legendre transforms. If, for example, we wanted to manipulate the pressure instead of the volume, it might behoove us to be able to define an auxiliary function which embodies that relationship more easily than manipulating the volume to affect a change in the pressure. So being more concrete, we can introduce other auxiliary functions by adding or subtracting those conjugate pairs. So in this case, if we take E plus PV, we'll end up with a auxiliary function which is a natural function of S, as energy is a function of S, but instead of V, it would be a natural function of P and N. E plus PV is a function you all have had exposure to before. That is the so-called enthalpy. We'll denote H. We could take E, subtract off TS, and additionally add PV such that we form a natural function of T, P, and N. E minus TS plus PV is what you would denote as G and call the Gibbs free energy. What if we did E minus mu n? That would give us some function of S, V, and mu. What would you call that? Have you run into that one before? It is a Legendre transform. It gives us access in a simple way to how the system changes as we manipulate mu instead of n. This doesn't turn out to have a common name. Wasn't something those thermodynamicists were thinking of back in the day. But still could be done. Okay, so summarizing all of those functions, we have the energy, which is a natural function of the entropy, volume, and number of particles. That means that differential changes in the energy occur through changes in the entropy, volume, and number of particles. What goes with N is mu, V is P, and S is T. We've defined a Helmholtz free energy, which instead of manipulating the entropy, manipulates the temperature, is a natural function of volume and number of particles, and thus can be constructed through a Legendre transform where E is less than T times S. The Helmholtz free energy then is a natural function of T, V, and N. What goes with N is still mu, V is still P, and now T and S have swapped positions, but they are still conjugate pairs, so they show up together. The Gibbs free energy is a natural function of the temperature, pressure, and number of particles, and thus can be constructed by swapping out the roles of T and S and P and V. Differential changes in the Gibbs free energy thus occur through changes in temperature, pressure, and number of particles. Mu goes with N, V goes with P, S with T, and the sign switches when I do those Legendre transforms. And finally, the enthalpy, natural function of S, P, and N, is thus constructed by taking the energy and adding back to it, PV. Differential changes occur through changes in S, V, and N with mu, V, and T. All right. A whole host of functions could be overwhelming to kind of keep track of, but if you remember the underlying mathematical structure by which all of these are generated, I think that one should not try to memorize all of these things. One should just understand the rationale behind why they all exist, and thus one could go off and rederive any of them just by understanding this structure. It's worthwhile trying to convince you of why it is useful to actually define all of these functions. So we've gotten some sense why it's useful to think about the Helmholtz free energy. It is a natural way to think about systems that can exchange energy. Why is it useful to define things like the enthalpy and the Gibbs free energy? Well, if I fix the pressure and number of particles, and I ask for differential changes in the Helmholtz free energy, in the enthalpy, that leaves me with T times ds. So if I go to this expression, I fix pressure and number of particles, I'm left with only T times ds. T ds is the reversible heat. So in fact, it is useful to define the enthalpy because if we work under conditions of fixed pressure, often do, set it to be atmospheric pressure, for example, if we fix the number of particles, also easy to do, keep the beaker closed, we can directly measure heat releases, and that is going to define a function, the enthalpy. So indeed, that's why enthalpy often is used to relate things like heats of formation, heats of reaction, etc. If P is not the reversible P, but just some applied constant, such that P initial equals P final equals some fixed P, the reversible work, or the work, if P is fixed, the PV work is just P minus times dV. dH is therefore dE plus P dV. Again, this is at fixed N, so there's no chemical work. dE is heat plus work. If N is fixed, there's no chemical work, there's only PV work, but PV work is just P delta V. So in fact, this is the heat released even in an irreversible process. Under conditions of fixed pressure and number of particles, even if we do the process irreversibly, we can tabulate the enthalpy by just measuring heat release. This is a useful quantity to define. If instead of working at fixed P and N, if we fix the temperature and the pressure, which is indeed very easy to implement experimentally, changes in the Gibbs free energy, Gibbs free energy being a natural function of temperature, pressure, and number of particles, is just mu times dN. So it is the chemical work. So at fixed temperature and pressure, the Gibbs free energy is a measure of how much energy is available to do useful chemical work. We could even generalize this if we had multiple kinds of particles and associated multiple chemical potentials, which quantify their ability to spontaneously change. dG at fixed T and P is less than or equal to 0 for a spontaneous change. So just as the Helmholtz free energy is something which spontaneously decreases in a spontaneous change, the Gibbs free energy at fixed temperature, pressure, number of particles is something which decreases in a spontaneous change under those circumstances. How can we rationalize that? So delta G can be written as delta H minus T delta S at fixed temperature and pressure. That is less than or equal to 0 in a spontaneous change. Well, that makes sense. If there was no delta H, we would expect that the entropy increases in a closed system with a spontaneous change. So minus that should decrease. Delta H is minus T times delta S of the surroundings. We've just convinced ourselves that the enthalpy is always the heat released from the system, which is minus the heat released into the bath. And if the bath is always at equilibrium, that is always a reversible change. So it is given by T delta S of the surroundings. So in fact, the Gibbs free energy is, in a very strict sense, only telling you about the total change in the full universe, in the whole isolated box from which we've carved out our system and partitioned it from our bath. It is just an incredibly useful way of codifying that change. Instead of having to keep track explicitly of the bath, we can introduce this Gibbs free energy, and it contained that same information. Okay, so that's some as to why we would introduce all of these other functions. Let's explore a little bit more about their structure, what we've learned, what we can define through their structure. So we have first derivatives of auxiliary functions. Things like how energy changes with entropy at fixed mechanical variables, which give us the temperature. We have how the Gibbs free energy changes with number of particle, for example, at fixed temperature and pressure. That's going to tell us the chemical potential. We could ask for how the Helmholtz free energy changes with temperature at fixed volume and number of particles. That will give us minus the entropy. So first derivatives of auxiliary functions, energy, free energy, enthalpy, they generate either the potentials for the transfer of energy, mass, or volume, things like temperature, pressure, chemical potentials, or their conjugate variables. So conjugate to temperature is the entropy, conjugate to the chemical potential would be the number of particles, conjugate to the pressure would be the volume. So there's always a simple definition that one can arrive at by taking a first derivative of an auxiliary function. Second derivatives, of course, have more structure. So let's explore that a little bit. Let's imagine taking the entropy and the derivative of it with respect to energy and doing that twice. Holding the volume and number of particles fixed. So that is the same as taking a first derivative of the derivative of entropy with respect to energy. That is defined as 1 by T. So if I work out that derivative, the temperature is some function of energy and entropy. So I could use the chain rule, I'll get minus 1 over T squared. And how the energy changes with temperature at some fixed mechanical variables inverted. How the energy changes with temperature is the reversible heat release over temperature. We would call that, or define that, as the heat capacity. dE dt, manifesting how the heat is released divided by temperature, is the heat capacity. So what can we say about the heat capacity from the second law? We know the second law tells us something about the relationship between the potentials for the transfer of energy and their conjugate variables. Increasing the entropy in a closed system depends on whether or not one part of the system is hotter or colder than the other part. Can we use the second law to say something about second derivatives, or for example, the heat capacity? Okay, let's go back to the setup of spontaneous partitioning. In an isolated system. So we've got our isolated system. It's wrapped in insulation, rigid and impermeable. Let's imagine starting with some energy localized on the left, E1, some other energy localized on the right, E2, and imagine that we allow for heat to begin to flow between one side and the other. We have convinced ourselves that the change in the entropy, if that amount of energy change is small, is going to be given by whatever the temperature on the left is, times the energy that moves from left to right, minus what the temperature is on the right, times that energy change, and then a spontaneous change of energy occurs through an increase in entropy. Let's take T1 to be hotter than T2, such that the change in energy, capital delta E, is positive. So heat flows from hot to cold. One to two in this case. And as a consequence, if heat flows from hot to cold, if we lose some energy from E1 and put it in E2, what happens to T1 and T2? It must be the case that T1 and T2 get closer. That if T1 is initially greater than T2, after I move some energy from 1 to 2, that T1 decreases a little and T2 increases. I start to heat up the cold side and I start to cool down the hot side. That means that dT dE at fixed mechanical variables is positive. As I move the energy over to side 2, as I increase the energy of side 2, it rises in temperature. If that was not the case, if I moved some energy over to E2 and it got colder, then I would move even more energy over to E2 because those temperatures would be even further apart. So rather than approaching equilibrium, I would move further away from equilibrium. In fact, for equilibrium to be stable, this must be the case, that the temperature increases with increasing energy. So in fact, we now have an inequality for the sign of dE dt. The sign must be positive or equal to 0. Mathematically, imagine an equilibrium partitioning of energy that we then go in and change by a little bit. So we have a system initially at equilibrium, and then I go in and I pull some energy to one side of the box. So we have entropy, which is a function of energy in the mechanical variables, that I can measure as I enforce or constrain that delta E to be finite. And I can compare that entropy to what it would be with the same fixed energy, same fixed mechanical variables, but in the original equilibrium system. By definition, it must be the case that the entropy lacking that constraint is larger than the entropy in the presence of that constraint. Equilibrium maximizes entropy, so if I go to that equilibrium system and I displace it from equilibrium by swapping some amount of energy, partitioning some amount of energy in a different way, I must decrease the entropy. Now, if that dE is small, I could write out an explicit expression for the change in the entropy. So entropy with the total energy and total mechanical variables fixed, and this repartitioning, delta E, is going to be equal to a first order bit or a 0th order bit when that delta E is 0, plus some first order correction, which is going to tell me about how the entropy of the different box sides change as I repartition that energy between one side and the other. Those are evaluated at dE is equal to 0. This would be nothing but 1 over T1, 1 over T2. At equilibrium, those temperatures are the same. So in the absence of that repartitioning, that reshuttling of energy from one side of the box to the other, that first order correction must vanish. So the second order correction, 1/2 delta E squared, now depends on the second derivative of the entropy of one side of the box with respect to energy on that side of the box, evaluated at fixed mechanical variables. Now plus, I get a squared, so the squared takes care of the original minus sign in the top part of the equation. How the entropy on the right-hand side of the box changes with energy on the right-hand side of the box. And we know that this whole thing has to be less than or equal to 0, because if I take this piece, it is greater than this total piece, than the total entropy. So if I subtract that off, I must have something that is overall negative. All right, so what is this second derivative quantity? Well, that's nothing but what we worked out a second ago. The second derivative of the entropy is minus 1 over T squared times the inverse heat capacity. So this is 1 over T squared, and the temperatures are the same because they're evaluated in equilibrium, CV to the minus 1. So what we've just found is that if I take a system, I displace it from equilibrium by a small amount, the fact that this has to be overall negative, well, the only way it could be negative, so 1/2 is of course a positive number, delta E squared, strictly positive number, minus T squared, strictly negative number, it must be that CV is positive. Has to be. Otherwise, that equilibrium state would not have been stable. So indeed, second derivatives, one can make sharp statements about the sign of second derivatives, which have real consequences because the heat capacity is a measurable quantity, and we've just learned that it has to be a positive number when measured. The same sort of approach would have shown that the second derivative of the Helmholtz free energy with respect to volume at fixed T in N is a strictly positive number. The first derivative of the Helmholtz free energy with respect to volume is minus the pressure. If that is, whole thing is necessarily positive, it must mean that dP dV is strictly negative, so that a negative times a negative is overall positive. So again, we have conjugate variables, P and V, have a definite sign of their change. Same thing was true in the heat capacity. The heat capacity was a set of conjugate variables, E and T. Their change with respect to each other has a definite sign. It's overall positive. These are all statements of pure second derivatives. Those that involve conjugate pairs. They will always have a definite sign. So S, if I repartition the energy, is a concave down function. It has a maximum. That maximum is the equilibrium value for fixed total energy in mechanical variables. A, the Helmholtz free energy, as I repartition the volume, for example, at fixed T and N, is something that is concave up, has a minimum at some equilibrium partitioning, and is a smooth function. All right. So indeed, one could continue Taylor expanding about that equilibrium and find that the second law, in fact, dictates that that auxiliary variables are convex functions. Their slopes are monotonically increasing or monotonically decreasing functions with respect to their natural variables. And that must be the case for the existence and stability of equilibrium. Just following generalizing these sorts of arguments. All right. What can we say about mixed second derivatives? For example, if I took the derivative of the Gibbs free energy with respect to pressure, which the Gibbs free energy is a natural function of pressure, temperature, and number of particles, and then took the derivative with respect to temperature, say at fixed pressure and number of particles. Well, the change in the Gibbs free energy with pressure is what we mean by volume. And so what we arrive at is a question about how the volume changes with temperature at fixed pressure and number of particles. Does it have a definite sign? Is it strictly positive, strictly negative? If I took a piece of metal and I heated it up, I increased its temperature. How does its volume change? Well, a piece of metal would expand. What about something like water? If I was to measure its volume as a function of temperature, say at atmospheric pressures, well, at high temperature, it would indeed expand. If you went past about 4 degrees Celsius, however, you'd find that it starts to contract. So the derivative, dv dt, has no definite sign. There are examples where it's positive. There are examples where it's negative. There are examples in the same system where it is both positive and negative. There's no law for mixed second derivatives, things of the form dv dt, variables that are not conjugate with each other. However, that doesn't mean that they're not fun. If we had a smooth function, if I took the derivative of f of x and y, for example, with respect to y at fixed x, and then x at fixed y, well, if it's smooth, I can change the order of those derivatives. I can take the derivative of f first with respect to x at fixed y, and then with respect to y at fixed x. So the Gibbs free energy, as we've just argued, is some smooth convex function. for the existence of an equilibrium state. That means we can take the derivative of G with respect to P at fixed T and N, and then with respect to T at fixed P and N. Or we can take the derivative of the Gibbs free energy with respect to temperature first, and then with respect to pressure. Does that generate anything interesting? Indeed, dG dP, we've just reminded ourselves, is nothing but V. I'm then asking how the volume changes with temperature, fixed pressure, number of particles. dG dt, on the other hand, is minus S. So I'm asking for how the entropy changes with pressure at fixed T and N. And now look at that. I've just found an equivalence between two seemingly very different sorts of experiments. I could measure how the volume increases with temperature at fixed pressure, and thermodynamically it must be that that is the same way the entropy changes with pressure at fixed temperature. This is a so-called Maxwell relationship. It is a relationship between two partial derivatives, between two seemingly distinct sorts of experiments that thermodynamically, because auxiliary functions are smooth, must give identical values. A fun example of the usefulness of Maxwell relationships, and indeed a lot of the structure we've just discussed, is to think about answering definitively which is bigger. The constant volume heat capacity, defined as T ds, again it's the heat, and how it changes with temperature at fixed volume, number of particles, or the constant pressure heat capacity, again the heat, TdS, and how it changes with temperature now at fixed pressure, the number of particles. Is that an answerable question? Does it have a definite relationship? Indeed, using this structure, we can demonstrate that it does. Now, the specific steps of this are a little complicated. It takes some intuition to know how to lay it out. You should be able to follow the individual steps, even though you might not necessarily have known how to string them together in this specific way. That comes with practice. Fear not, you'll have ample time to practice such things in many homework examples. Let's try to answer this question by considering the entropy as a function of V, T, and N. Now, the entropy is not a natural function of V, T, and N, but we can nevertheless express it as one. If we do, we have changes in the entropy occur through changes in temperature, volume, and number of particles. The way the temperature changes the entropy is through ds dt at fixed V and N, through the volume through ds dV at fixed T and N, and through the number of particles through ds dN at T and V fixed. Now ds dt at fixed V is the heat capacity up to a factor of 1 over the temperature. ds dV can be related through a Maxwell relationship. So T, V, and N, those are natural variables for the Helmholtz-free energy. It will behoove us to write that down. Helmholtz is minus S dt minus P dV plus mu dN. ds dV connects dP dt. So ds dV at constant N and T is equal to dP dt at fixed V and N. That's a Maxwell relationship. So if I multiply this first equation by T, I have T ds. Let's fix N is equal to CV over T. Plugging in our Maxwell relationship, we have dP dt at fixed V and N, dV at fixed N, dN at fixed N is 0, so we can drop that. If we divide, sorry, I have a dt missing. If we divide through, let's clean that up, sorry. If we divide through by that dt, we'll have T ds over dt. If we fix P, that will give us the constant pressure at heat capacity. Multiplying through by T. And I'm left with T dP dt, constant V and N, dV dt, constant N and P. So we have a relationship now between the constant pressure and constant volume heat capacities, which is temperature, typically positive, not always, but typically, and some stuff, dP, dt, dV, dt, that has no definite sign. There's one more trick that's useful to introduce, which is the so-called cyclic chain rule. Which lets me write dP dt at constant V and N as dP dV, constant T and N, times dV dt at constant P and N up to a minus sign. If I plug that in for dP dt, I have now Cp is equal to Cv plus minus T times dP dN, constant T and N, times now 2 factors of dV dt at constant P and N, dV dP has to be less than or equal to 0 for stability. Those are conjugate pairs. Their relationship has a definite sign. This, something squared, strictly positive. So what we've just deduced, provided we're in a stable system, the temperature is positive, that Cp is greater than CV. Again, a somewhat silly exercise, but something that you can derive through the mathematical relationships we've elucidated through this lecture. The introduction of stability requirements and Maxwell relationships, and a last little trick known as the cyclic chain rule. So I will be happy to discuss this in more detail and to go through it again in our live session, play around with other sorts of mixed and pure derivatives. And so I'll look forward to your discussion later on Tuesday. All right, everyone be well.